9. All of this stuff, all of these rigid bodies, you just really want to get used to the flow of the stuff that every rigid body problem has in common. Those are those 6 steps where 5 is maybe yes, maybe no, you know? And every problem is going to have those steps. And it's just getting to those steps and then what you do after the steps. Okay, so no gravity. The rectangle, we have dimensions, density, thickness. Okay, it does give some angles, but it turns out that the angle it gives doesn't matter at all, because you can just use this coordinate system and that's the end of it, you know. You never have to change coordinate systems or anything like that. Okay, do you understand what I mean? Like, if you had to later express stuff in our usual coordinate system, then rotation matrices would help. But if you can just express stuff in this coordinate system the whole time, then, you know, so like, once you have, so you have this body in this coordinate system, what's the difference? Like, how do you go from a calculation of this in this coordinate system to a calculation of a straight thing in a straight coordinate system? The answer is, it's like a trick question, like a joke question, but the answer is you turn your head a little bit, okay? Like, that's all, like, this is the same thing as a straight, you know, it's the exact same problem as this thing being straight and the coordinate system being straight. Okay. At A, so I'm going to move this over here. And so free body diagram. Come on. Okay, so over at A, we have, oh, well, okay, so I gave these vectors, and so this is sort of an interpretation thing. I mean, I guess, so what I just said, all that stuff, I mean, if these are intended to be, whoever wrote this problem did not, that's a joke, wasn't very clear about, you know, what I was asking. If these forces are in the coordinate system I drew, then we're good. If these forces are in our usual coordinate system, then yeah, we have to use a rotation matrix in order to re-express these forces, or do a ton of trigonometry. And if it doesn't give a coordinate system, it's probably always best to assume that it's implied that that's a horizontal vertical coordinate system. So I apologize for saying you didn't need a rotation matrix.
But I think that includes the 40 degrees from...
Yeah, right. Okay, so yes, I agree that you are correct about all that. So in this coordinate system, so let's think about rotation matrices. So to rotate the coordinate system, theta, an angle of theta counterclockwise, you're going to use a rotation matrix like this. This always works. Cosine of theta, sine of theta, negative sine of theta, cosine of theta. And so calculate that matrix, and then you can just multiply it. Your calculator will do it. So then this matrix on the left multiplied by any vector in the old coordinate system gives you the vector in the new coordinate system. Okay, so if we want to, so in our case, we're given these force vectors in a coordinate system like this. And we want to express them in a coordinate system like this. Then you have to think about the counterclockwise angle to go from the one on the left to the one on the right. You know, this is the old, this is the new. And the easiest rotation is just 40 degrees clockwise, which makes it a negative angle. So this theta is negative 40. Okay, so this rotation matrix is cosine of negative 40, sine of negative 40, negative sine of negative 40, cosine of negative 40. The short answer on this question, by the way, is don't worry about this rotation matrix stuff, but I'm going to show it to you because, so sorry about assigning this. That was something I planned to sort of phase out this semester, and I gave you that problem anyways. But okay, this rotation matrix, still this is good stuff to see. So this is 0.766, negative 0.643, positive 0.643, positive 0.766. So that's our rotation matrix. Yes?
Yeah, in the problem it says 40 degrees from vertical, so wouldn't that make it 50 degrees?
From vertical, yeah, yep, you're right. So 40, wait. At the long dimension, oh yeah, so this, thank you. This is 40 degrees. And so, yeah, so maybe let's do this coordinate system instead. And then that makes this positive 40. Does everyone see that? Now it's like my new coordinate system. That makes it a counterclockwise rotation. That makes all these positive angles. And that switches the signs of these. Okay, and now, so the force at A is that Q matrix times the vector negative 200, negative 150. Does anyone have a TI-89 in here that I can use? I'm gonna just run and get my calculator. Okay, yeah, if you could calculate that, I'll be back in 30 seconds. Okay, so, thanks. Okay, so the first one is negative 249.65, 13.70. So that's expressed in the new coordinate system. And then the one at C is Q times negative 400, positive 300. And you get negative 400, 300, negative 113.5, 487.0. And then the last thing it gives us is the velocity at the center of mass. This works for any vector, not just force vectors. So the velocity of the center of mass is Q times 5 negative 3 and that's negative 1.901 and negative 5.513 meters per second. All right, so now we have all of our vectors re-expressed in the new coordinate system. And we know that the angular velocity is negative 6. Do we have to re-express that angular velocity? Yep.
I'm sorry, but what are you multiplying Q by to get the new values?
The vector value in the old coordinate system.
Okay.
So that Q matrix times, this is the force that was given. Yeah.
Okay.
So that's what I'm doing. You do not have to do this. You do not have to do this stuff. And I'm sorry if you wasted a lot of time on your homework, but these rotation matrices are a really useful thing. In D-form, we use them all the time. In statics, we use them a little. So can't hurt to see it, but I should not have assigned this problem. Okay, so what about the angular velocity? Well, remember that's a that's a z component of a vector. And so if you're rotating a coordinate system about the z-axis, it's not going to change that z component. So we don't have to rotate that. That value stays the same. All right, so our new thing is like this. I'll draw the free body diagram. So we have a force vector over here of negative 249.65, 13.70. And we have a force vector here of negative 113.5, 487.0. Okay, so the first question is, what's the velocity vector of the point A? Well, it asks the velocities of A and C. So for both of those, we're given the velocity of the center. Okay, so anywhere you know the velocity or you know the acceleration, you're going to use relative motion with that as sort of the intermediate point. Okay, so we can think of it as the velocity of A relative to the ground, which is what we want, is equal to the velocity of A relative to the center of mass plus the velocity of the center of mass relative to the ground. And the reason we do it that way is because this is what we're given, the velocity of the center of mass relative to the ground. So the velocity of A relative to the center of mass, you can always think of that as like, it's like treating it like the point you're relative to is fixed, and it's just a rotation of the thing around that fixed point. So this is equal to, we're going to use the circular motion equation, so omega cross r. Omega is 0, was it -6? Yes. And r, now that we're in this more convenient coordinate system, is just going from the center to A. So what are the dimensions? 2.1 and 1.3. So it's half of 2.1 in the positive y direction and half of 1.3 in the negative x direction. And then 0 for z. So the velocity of A relative to the center of mass is equal to 0, 0, -6, crossed with -0.65, 1.05, 0. So for x, we get 6.3. For y, we get positive 3.9. 0 for z. Now put it back into the relative motion equation. Whoops. So the velocity of A relative to the ground is 6.3, 3.9 plus negative 1.901, negative 5.513. So basically 4.40 negative 1.61. And you do the same thing for the velocity of the point C. You just use a different R vector. But let's go to the kinetics part now. So what's the acceleration of the point B at this instant? So in order to do this, we're going to need to do the kinetics to calculate the acceleration of the center of mass and the angular acceleration. So we're just getting right into the 6 steps of rigid body kinetics. So step 1 is there a fixed point? No, correct? And so the about point is the center of mass. Now we can calculate the moment of inertia about the center of mass. That's 1/12 times it doesn't give a mass, it gives a density, but we have the volume, so this is going to be, so before I do this, we have to calculate the mass. So the mass is 2,500 times 2.1 times 1.3 times the thickness of, was it 0.1? What's the density of 2,500? Where does that fall in the densities of materials? Like, is that less dense than a feather or as dense as a neutron star? Or like, what is that? Any ideas what densities are of like common materials? In SI units, the density of water is 1,000 kilograms per meter squared. So this is bigger than water. The density of steel is 7,000 kilograms per meter squared. So somewhere in that ballpark of like engineering materials we're used to.
Maybe graphite.
I don't know, but somewhere in there, So the mass is 682.5 kilograms. And now we can calculate the moment of inertia. 1/12 times 2,500 times 2.1 squared plus 1.3 squared. And so that is 1270.83 kilogram meters squared. Yep.
Why are you multiplying by 2,500? Is it math?
Yes, it's mass. I'm sorry. That's why we went through all that. $682.5. Okay, so this is 346.94. Okay, now free body diagram. I guess I did that above here. I'll just move that down. And now I can, step 4, write out the table, row force moment. We only have 2 forces on here. The first one is at A in the upper left. So now our about point is the center of mass. We figured that out in step 1, that our about point had to be the center of mass. And so our row vector is from the about point to the point where the force is applied. So that is negative 0.65, positive 1.05. The force vector is negative 249.65, 13.70. And the cross product is 253.23. And then the force at C, well, that's just the opposite corner, so that's just going to be the opposite of this, 0.65, negative 1.05. And the force vector is negative 113.5, 487.0. And you get positive 197.38. Is there a fixed point in this for this problem? I mean, we already had to think about that in step 1. There's no fixed, and so that means we have to use Newton's second law. And so Newton's second law says add up these force vectors here. So negative 249.65, 13.70, plus negative 113.5, 487.0 is equal to the mass, 682.5, times the acceleration vector of the center of mass. So we can use that to calculate AX is equal to negative 0.532. And AY is equal to 500.7 divided by the mass. Positive 0.734. Okay, so the acceleration of the center of mass is negative 0.532, positive 0.734. And now the moment equation, 253.23 plus 197.38 is equal to 346.94 times alpha. So positive 1.299. And so that gives that as a vector, alpha is 0, 0, 1.299. Any questions about that? So now what we're trying to calculate is the acceleration of the point B. That's this one down here in the lower right. So the acceleration of B relative to the ground is the acceleration of B relative to the center of mass plus the acceleration of the center of mass relative to the ground. This one we know from Newton's second law. Okay. The acceleration of B relative to the center of mass is, we're going to use the watermelon equation. Alpha is 0, 0, 1.299. Omega was negative 6, right? And the R vector goes from the center of mass, the about point, to the point we care about. So that is negative 0.65, negative 1.05. Okay, so 0, 0, 1.299 crossed with negative 0.65, negative 1.050, plus 0, 0, negative 6, crossed with the quantity 0, 0, negative 6, cross negative 0.65, negative 1.050. everything below here is useful. Okay. Any other homework problems you want to talk about? Let's see. Do we have time to do one rolling problem? I would like to do that.
I have two hopefully quick.
Okay, yeah.
Number 10 for the answer key, I think you pointed from your point A to your pin rather than the
Oh,
center mass
okay.
pin.
Right.
Should it be from the center mass pin for inertia?
For moment of moment of inertia. It doesn't really matter for moment of inertia because it's all you're just squaring stuff, so it's just distances for moment of inertia. For the r vector or for the rho vector, it would matter if I did that in calculating my moments.
I think a moment of inertia is correct term. When you were looking at the base inertia for the circle
Yeah.
plus the displacement.
Yeah.
The displacement was pointing from A to the pin.
Oh, okay, right. Yes, you're right. It should be from the center. Yeah. It should be yeah, this is the distance that you need for the parallel axis theorem. And then was there another question?
Number 3 on the weekly,
Mhm.
you need a radius for the entire stuff. Should we, it's not given, should we just use R as a variable and carry that through for our answer?
Let me give you a value.
So, is it 0.1 or 0.01?
I did say, I think I said, let me, okay, so let me, number 3? No. Which number? Number 5?
That's
For
what
the
the from.
written assignment, this is
The old one.
Oh, that's the first one. Oh, yes. What did I say? Yeah, let's go 0.1.
It says right there, 0.1.
Oh, you are looking at an old, no, yours didn't have that. And I think after I talked to Nicole, I put it in there. And, okay. Anyways, 0.1. Okay, we don't have time to talk about rolling. I'll start that next time. So, okay, have a good spring break, everybody.
You too. Thank you.
Get a good snow tan.